All right, we're going to do a 15.3 supplement. And we're going to derive the conservation of energy. So like I mentioned in class today, we've been talking about conservative fields, and we might wonder what they conserve. If we look at this in terms of physics, in terms of Newton's laws, we can say that conservative fields conserve energy, and we're going to use line integrals and vector fields to come up with a conservation of energy. So to do that, we're going to say that F is a conservative field. And this field moves an object along some path. Our path C, which is given by some R of t. Between times A and B. A is less than or equal to t, less than or equal to B. And we're going to say that the position R of A is capital A, and R of B is capital B. Just to simplify our notations. All right, so Newton's second law. Newton's second law says that if we have some force, and F is a conservative field, we're thinking of F as some kind of force, because it's moving an object along a path. So the force as a function of position, F of R of t, is the mass times R double prime of t. Force equals the mass times the acceleration. So force at our position equals mass times the acceleration at that particular parameter, value of the parameter t. So our work. The work done moving our path along this, or moving our object along this path, we say W equals a line integral of f dot dr, and we're going to evaluate this by taking the integral from a to b of f of R of t dot R prime of t dt. So that's our, I need an extra parentheses. There we go. So that's our work. And f of R of t is m R double prime of t. So our work equals the integral from a to b of m R double prime of t dot R prime of t dt. Now this quantity R double prime t dot R prime t. Let's look at the derivative, the time derivative of a dot product. We're going to look at the time derivative of R dot R. When we talked about taking derivatives of vector value functions, we talked about a chain rule. So this is going to be our product rule, I'm sorry, not a chain rule. R double prime dot R prime plus R prime dot R double prime. So the derivative with respect to time of R prime dot R prime is 2 R double prime dot R prime. And it was a while back that we talked about this, but we did talk about this product rule for derivatives of dot products. So looking at this quantity here, we have R prime dot R double prime dot R prime. So this is the same. Our work is equivalent to m over 2, the integral from a to b of d dt of R prime dot R prime. So I'm just substituting this quantity in for R double prime dot R prime. And R prime dot R prime is the magnitude of R prime squared. So we get that this quantity is m over 2, the integral from a to b, of the derivative, time derivative, of the magnitude of R prime. And I'm going to drop the t's. Magnitude of R prime squared. We know that R depends on t, so I'm just going to drop that just to clean this up a little bit. Well, now we're taking the definite integral of a derivative, so we can use the fundamental theorem of calculus to say that our work is m over 2 times the magnitude of R prime squared evaluated on t equals a to t equals b. And if I write this out, we're evaluating R prime at the endpoints. This is m over 2 times the magnitude of R prime of b squared minus the magnitude of R prime of a squared. And R prime of b and R prime of a, R prime is the velocity. And I need another parentheses around here because m over 2 is multiplying the entire thing. So I could write this as the velocity. So this equals, and I'm going to write it in a more familiar notation for those of you that have been in physics before, 1/2 m the magnitude of our velocity squared at position at parameter t minus 1/2 m times the magnitude of the velocity at a squared. This is the change in the kinetic energy. So the work done, moving our particle along that path from t equals a to t equals b, equals a change in the kinetic energy along that path. And I'm going to write that as the work equals k of b minus k of a. Put kinetic energy at position b, we set up here, and minus the kinetic energy at position A. Change in the kinetic energy. So there's one expression for the work that we've done in moving that particle along that path. So what we're going to do is come up with another expression for the work and equate the two. So one of our expressions is that the work is the change in the kinetic energy. All right, so we're going to assume that F is conservative. We're assuming that we have some kind of conservative force field. So we know that F is the gradient of some scalar potential function. And we're going to call this potential function, in this case, our potential energy. We're going to call our potential function the potential energy. In physics, we call the potential P at some point the opposite of x, y, z. So our potential energy P in physics is the negative of our potential function that we've been talking about in class. So P equals negative F. So in our notation here, we would say that F is negative del P. And this is just a convention that we use that's different in physics from what we do. So we want to keep this straight because we're talking about this in the context of physics. Our work, the work done by this conservative force field moving our particle from A to B, we're assuming that F is conservative. So our work W is the line integral along C of F dot dr. And that we're going to say that that's just the opposite of del P dot dr. And by the fundamental theorem of line integrals, this is just the potential evaluated at A, potential evaluated at B, and the difference. So this is minus the potential at our position B minus the potential energy at position A. And that is potential energy of A minus potential energy of B. And we're going to equate the two expressions for work. So we're going to say that potential energy of A minus the potential energy at B equals, and our previous expression for the work was the kinetic energy at B minus the kinetic energy at A. And I can rewrite this and say that the potential energy at A plus the kinetic energy at A equals the potential energy at B plus the kinetic energy at B. And what this is telling us is that if we have a conservative field, conservative force field, our field is doing some work on a particle moving from point A to point B, the sum of the potential energy and kinetic energy is constant. And this is the conservation of energy. In this conservative force field, the energy, the sum of the potential and kinetic energy, all the energy that this particle has, or this object has, is constant as it moves through this conservative force field, if the force F is the only force that's working on the particle. So this is assuming just that our field is conservative and that Newton's second law is true. we come up with the conservation of energy. So that's starting from really some basic assumptions. That's a pretty amazing thing to be able to come up with from those assumptions.